Okay, so welcome to this tutorial on radioactive decay. This is for GCSE level. We're going to go through what we're talking about in this tutorial in just a second, but to start with I want to pose you this question just to check that you can remember what we've done in previous lessons. So the first thing to check, here's a illustration of a model of an atom and here's an illustration of a model of another atom. Can you tell me which type of atom it is, which element it is? Can you tell me whether it's an atom, an ion, an isotope? Can you tell me the atomic number, and can you tell me the atomic mass number? Okay, so maybe press pause on the video, see if you can work that out, and then we'll move on. So now that you've done that, in this video on radioactive decay, we're going to try and answer 3 key questions. First of all, why do some nuclei undergo radioactive decay? Not all atoms are radioactive, so why are some radioactive and why are some not? Second of all, what is radioactive decay? We need to be able to define it. And thirdly, what are the different types of radioactive decay that can be produced when a nucleus decays? So let's have a look at the answers to the question that I say on that very first slide. If we have a look at this atom, first of all, if we count up the number of protons in the nucleus, we've got 6. And any atom that's got 6 protons in its nucleus is the element carbon. Now we know that this is an atom because as well as having 6 positively charged protons, we've got 6 negatively charged electrons. So the overall charge of this is neutral, so it's an atom. Now that means the atomic number of this is 6, which makes it carbon. And if we want to find the mass number, we have to count up the total number of protons and these blue neutrons in the nucleus, and if we add that up we get 12. So this is carbon 12. It's carbon because it's got 6 protons in it. So this is our standard carbon atom that you find in most materials that we see. If we have a look at this second atom over here, and we have a look at first of all what type of element it is, we count up the number of protons and we find that we've got 6 again, which makes it carbon. So the atomic number is 6 and it is an element of carbon. If we look at the charge, again, we've got 6 electrons balancing out the charge of those 6 protons. So it's an atom, not an ion. But if we count up how many neutrons and protons we've got in the nucleus, you can see on this one here, we've actually got 8 neutrons plus the 6 protons, which means we've got a mass number of 14. So this is carbon 14 with 6 protons, and this is an isotope of carbon because it's got a different number of neutrons in its nucleus. And it's really important that we've got these ideas really clearly in our mind before we move on to think about why it is that this nucleus turns out to be radioactive and this nucleus is not radioactive. So now we're moving on to answering our first question, which was why do some nuclei, and by nuclei I mean that's why do some nucleuses of atoms, why do some nuclei undergo radioactive decay? So first of all, we have to have a little think about the forces that are acting inside a nucleus. So first of all, I've got this question for you. What should these positively charged protons be doing to each other? Do positive charges repel one another or attract one another? How is it that they can all stay in this really small tiny space within the nucleus? How is that even possible? What forces are going on there? So could you just have a little think about that for me and press pause, have a think, try and answer the question and then press go again. So we know from our work on electrostatic forces that we did in our electricity topic that positive charges repel other positive charges. So all of these protons should be repelling each other because they're positively charged. And that means that they're exerting forces on one another, pushing each other away. But we know that within the nucleus, we've got all of this mass confined to this really small, dense part of the nucleus. So there must be something else going on that we're not quite aware of at the moment. And it turns out that there's another force acting that we haven't yet seen in physics that we're learning about now for the first time. And the name of that force is the strong nuclear force. And I've got some video clips here to show you, to give you an idea, like a model to imagine what the strong nuclear force is doing. So if we have a little look at this video clip, I've got 2 magnets, 2 bar magnets, and they're covered in Velcro. Okay, so you can see here and here we've got Velcro around them. And I've got two like ends repelling. You can see that as I move this magnet closer to this magnet, it pushes it away. And this is just like the positively charged protons. They actually want to repel one another because they're positively charged. But if we have a look what happens here, if I can get the magnets close enough, then I can get the Velcro that surrounds the protons, or in this case the magnets, to attach. And in that case, the Velcro is strong enough to keep the two repelling magnets away. But Velcro only acts over really short distances, but over those short distances it's very, very strong. And that's just what the strong nuclear force does. The other thing to look at here is that a neutron, which would be represented by this block of wood, also has the strong nuclear force. It also has this Velcro around it. So neutrons can exert the strong nuclear force onto other protons and help stick everything together with this essentially sort of nuclear Velcro, this strong nuclear force. So if we're going to hold a nucleus together with all of these protons and these neutrons, we need to get the protons close enough to the other protons and the neutrons so that the Velcro can act, so that the strong nuclear force can act. And if we can do that, then we can get the nucleus to stay together and not repel each other. But we're going to need to get them really, really close together, and we're going to need a lot of Velcro. So the more protons we have, the more Velcro we need, the more strong nuclear force we need, which means we need more neutrons. And in this example here, the wooden block is acting as a neutron. So what we need to think about now is that when we're thinking about whether a nucleus is going to decay or not decay, we have to effectively start thinking about the different nuclei in the atoms as either stable nuclei or unstable nuclei. And by that I mean either all the forces are balanced and the protons and the neutrons are happy being together, or they're not. So in an unstable nuclei, there's not enough strong nuclear force, or there might, to balance out the positively repelling protons. And in a stable nuclei, all the forces are happily balanced and the nucleus is really stable. And it's really important to remember that all unstable nuclei want to become stable nuclei. That's what everything is trying to get to, for this unstable nuclei to become more stable. So things that would make an unstable nuclei unstable, if it's got too many neutrons, if we remember seeing that block of wood with the Velcro, if we just kept adding blocks of wood, that wouldn't make the nucleus any more stable. So if we've got too many neutrons, it's unstable because those neutrons want to sort of go off somewhere. And if we don't have enough neutrons to keep those positively charged repelling protons together, then it's going to be unstable. But in a stable nuclei, we've got just this right balance between the positively charged protons and the neutral neutrons, and that strong nuclear force acting between them to hold it all together. So now we're ready for our second question, our definition of radioactive decay. What is radioactive decay? So radioactive decay is the nucleus gives out radiation as it changes to become more stable. This is a random process called radioactive decay. So that nucleus that we were seeing before, it's going to change and give out radiation in order to become more stable. And this leads us nicely onto our third and final question. What are the different types of radioactive decay? So these are the things that are given out by the nucleus as it is decaying, trying to become more stable. So let's have a little look at what we've got. There are three key types of radioactive decay that can be given off by an unstable nucleus: alpha, beta and gamma. Now our exam board also wants you to recognise that fast moving neutrons can be given out by unstable nuclei, but that depends a bit on your exam board as well. So generally, if we're talking about the three types of radioactive decay, we talk about alpha, beta and gamma, and we'll be looking at situations involving fast moving neutrons later in the nuclear course. So let's have a look at alpha to start with. Alpha decay, this is the symbol for alpha that we're going to use, and it consists of two neutrons and two protons, so it's a helium nucleus. Okay, that's what the decay particle is. So the nucleus that was unstable gives out two protons and two neutrons, and it just gets rid of them. This radiation is really ionizing, really, really ionizing. But because it's so ionizing, it can only travel a few centimetres in air. So you have to be really close to this type of radiation for it to be dangerous. If we now look at beta decay, and this is the symbol here for beta, beta is a fast moving electron. See, so it's going whoosh. Yeah, it's a great illustration. Beta decay is ionizing, but nowhere near as ionizing as alpha decay. And it can travel further because it's less ionizing. So beta decay could travel tens of centimetres in air, sort of up to a metre maybe, but more on a scale of tens of centimetres in air. But it's not as ionizing as alpha decay, but it can travel further. And then if we look at the third type, gamma radiation, this is our symbol for gamma here. Now gamma is a bit different. Gamma radiation is a type of electromagnetic radiation. It's travelling as a wave at the speed of light. It's not very ionizing. I mean, it is compared to other things. It's still not terribly safe, but it's far, far less ionizing than the alpha particles that we've seen up here. But it can travel much, much further. It can travel meters in air. So you have to be much further away from a gamma source because it can travel so much further. So as well as being different things, so we've got our helium nucleus here, the 2 protons and the 2 neutrons, got our fast moving electron, and we've got our electromagnetic radiation here travelling as a wave, and them having different ionizing properties. So remember, alpha particles are very ionizing, beta particles are a bit ionizing, and our gamma radiation is less ionizing still. They have got different penetration abilities. So alpha particles can't travel very far. If you put a sheet of paper in their way, that will stop them. Beta particles can travel through a sheet of paper, but they will be stopped by a sheet of aluminium metal. Gamma radiation can travel through a sheet of paper and through a sheet of aluminium, and it will need either a piece of lead a few centimetres thick or several metres of concrete to stop it. It's far, far more penetrating. So there's this trade-off between how ionising something is. So alpha is the most ionising but the least penetrating, whereas gamma is the least ionising but the most penetrating. So it's this trade-off between the 3 different types of radioactive decay here. Now these properties, the ionising properties and the penetration properties, you must learn and remember because you're going to be asked to apply them to different scenarios. So that was a quick introduction into why some atoms undergo radioactive decay, and hopefully now you should be able to answer these 3 questions. So it might be worth pausing, having a look at them and see if you can answer any of them. If you can't, go back and watch that bit of the video again, and then if you've got any questions, add them to the question document during the lesson. So first of all, first question, why do some nuclei undergo radioactive decay? Second, what is radioactive decay? And thirdly, what are the different types of radioactive decay that might be emitted? I hope that was helpful. Any questions, let me know, and I will see you soon.